Okay, I'm back. Actually, you could probably hear my voice because I had my microphone off for part one. It was a little frustrating. I'd love to make a new video for part one with sound, but I'm just not going to have the time to do it, so you'll just have to kind of just watch the motions from part one as I work this one up. But hopefully you can hear me now. Here's part two. Uh, Part two, what we have here is a word problem where we have to solve three equations with three variables. Now, here I mentioned that a single counts as one total base, a double counts as two total bases, a triple has three total bases, and a home run has four total bases. It's kind of like a monetary value if you want to think of it that way. Like, a kind of ticket costs this much money, another kind of ticket costs another kind of dollar amount, whatever. Here we're talking about Barry Bonds. Did not hit any triples, but he had 94 singles, doubles, and home runs. So obviously we'll make this X, Y, and Z. So that's simple. X plus Y plus Z equals 94. He had 192 total bases. Well, each single counts as one total base. You're told that. So it's 1 times X. Each double counts as two total bases. That'll be Y. Each home run counts as four total bases. Home runs are Z, so 4Z equals 192. And then you said the number of singles is 10 more than doubles and home runs combined. So singles, that's X, is, was means equals 10 more than that. So really the best way to do this problem is to substitute. Probably helps to label the equations. So 1, 2, 3. So let's sub 3 into 1. So you have 10 plus Y plus Z plus Y plus Z equals 94. Clean it up. 2Y plus 2Z equals 84. And I think I did that right. Okay. Then you want to sub 3 into 2. And now you get 10 plus Y plus Z plus 2Y plus 4Z equals 192. So you get 3Y plus 5Z equals 182. So now we got two fresh equations, but with just two variables. We can solve this. We would change up colors just for some contrast. 2Y plus 2Z equals 84. 3Y plus 5Z equals 182. Let's multiply that by -3. Multiply that by +2. I wish to get rid of Y. You could wish to get rid of Z, your choice. Now I want to use elimination, so -6Y minus 6Z equals -232. 6Y plus 10Z equals 364. You get 4Z. Using a calculator, you probably should have done a calculator when you're doing these calculations. I'm just trying to use my head. But it's better to use a calculator just to be safe. Because otherwise, if you get a mistake, then you don't know what's going on. I think it's 132. So Z should equal 28, I believe. What do you think about that one? Actually, I'm going to use a calculator. Let's be smart about this here. Okay. 1 sec. Okay, I must have made a mistake somewhere because I know this doesn't make any sense. What I just have 84 times 3. Aha! That's why you should use a calculator. That's 252. The reason I know that is because I'm a baseball fan, and I know Barry Bonds did not hit that many home runs in 2007. Okay, so then we get 28. Alright, cool. Now we're in business. So you get Z, then you can let's use green. Then you can get Y. Say we do 3Y plus 5 times 28. So let's say you have to be very methodical about this. 140. So Y equals 14. So you have 14 doubles. And remember X this is so frustrating sometimes. Why does it not erase? Okay, let's use orange. X will equal 10 more than doubles and home runs, which will be 52. So we have all three answers now. Singles, doubles, home runs. So that's how you solve number 1. For number 2, a lot of it's just stating things. Like in this case, assign your variables. Clearly we want to solve for the number of mini and regular piñatas. So we'll let X equal a number of mini piñatas and Y equal a number of regular piñatas. The objective function, that's your goal. Your goal is to maximize the pieces of candy. So we'll call it N for number of candies. You could use any letter you like. You could use P for pieces of candy or C for candy, whatever you. I don't really care. But you want to maximize the number of candies, so it has to be X plus Y. Constraints, we've always talked about this. You can't have negative number of candies, so you got to have X greater than or equal to 0, Y is greater than or equal to 0. And what are we limited by? We're limited by hours of labor, and we're limited by costs. So if I look at the hours, 2 hours and 3 hours for mini and regular respectively, and we only have a total of 150 hours of labor available. And the other one, candy. Sorry, I'm losing my mind. Cost of candy, 100 pesos and 200 pesos for mini and regular respectively. I guess I just really like candy a lot, so I'm probably just want to eat some candy right now. So 100x plus 200y has to be under 8,000. And you know what? I'm kind of really losing my mind because each piñata has a different number of candies. We want to maximize the number of candies, not the number of piñatas. So I was wrong. The objective function is not x plus y. It's 100x plus 210y because, again, that's the number of candies from each one. You want to maximize the number of candies. So we have to figure out how many piñatas to make and then figure out the candies from that. Okay. Now you want to graph the objective function. Sorry, graph the constraints. And here's what we'll do. Let's find the x and y intercepts for each of these. Uh, 75 and 50. For the that constraint that dealt with hours, and then it will be 80 and 40. It'll make the graphing a lot easier if we find x and y intercepts. Okay, so 75 and 50. So we locate 50 for y intercept, 75 for x intercept. Connect those two. We'll shade below. Next one's going to be 80 and 40 for x and y intercept. So here's 80 40. So we kind of like that. And of course, we're going to shade only in the first quadrant. Now, if you think about the vertices, clearly we have a vertex at 0, 40. We have one at 75, 0. And then we want the point of intersection. I'll label as POI, point of intersection. If you use your calculator, use the solve 2EQ program that I've given everyone in the calculator, you can actually use the solve 2EQ to get x and y. And you'll find it'll be 60, 10. I know my graph doesn't represent that clearly because I'm kind of drawing this a little bit carelessly, but that's what you would get. And of course we have vertex at 0, 0. Remember, we have to be in the first quadrant because x is greater than or equal to 0 and y is greater than or equal to 0. So here are your vertices. Just state them 0, 0, 0, 40, 75, 0, 60, 10. And then to find the right combination, you want to plug in each vertex into the objective function. And if you do that, you will get 0, 40 as the highest one, because n will equal 100 times 0 plus 210 times 40, which is 8400. So this gives, so you want 40 regular pinatas. And that'd be the right way to do that problem. If you tried the other ones, they wouldn't quite get you the maximum number of pinatas. Let me stop the video again, because it looks like I'm going to need a little more time to finish up the rest of this test. So I'll do a third part here.